Hello everyone. Now that the midterm is over, we're transitioning to 4Ps analytics. So we will be focusing on the 4Ps in marketing: price, place, promotion, and product. And in this lecture, we will start with price, the most day-to-day maneuver in the marketplace. Hello everyone. Welcome back to Marketing Analytics. In this lecture, we cover price optimization. In this video, we're going to cover the demand curve and how does profit vary with price according to a linear demand curve, and how to solve price optimization problems using Excel's solver. And then we're going to talk about a specific form of pricing commonly used in marketing called product tie-in pricing. First, what is a demand curve? In particular, we're going to look at the simplest form of demand curve. Well, in fact, we are actually talking about a linear demand curve. So in this illustration, we can see that price is the horizontal axis and demand is the vertical axis. The demand is formulated as a linear function of price. That is, demand equals 390 minus 0.1 times price. So if you draw the relationship between price and demand in this system, what you're going to get is going to be a downward sloping straight line. And that is what we call a linear demand curve. Let's take a better look at what this demand curve implies. First, if the price is 0, when price is 0, 0.1 times 0 is still 0, so it will be 390 minus 0. Which means when price is 0, demand is actually 390. It basically says the market size is 390. And even if you lower the price to 0, only 390 people are going to get the product. On the other hand, what if the demand is 0? When the demand is 0, we have 0 equals 390 minus 0.1 times price. So if demand is 0, that price level that leads to a 0 demand should be 3,900. So 3,900 times 0.1 is 390, and 390 minus 390 is 0. So the point of 0 demand corresponds to the point where price is 3,900. So you can imagine the scenario of 3,900 is a price level where nobody is willing to pay a price higher than this in the market. So when you raise the price to that point, your demand drops to 0. So that's where the demand curve is at both ends, either 0 price or 0 demand. And if you have a point in between, let's say $100, what if the price is $100? And the demand curve would help us find out at a price level what the demand is. Analytically, we can plug in the price of 100 here. So 100 times 0.1 is 10. And then the demand would be 390 minus 10, that's 380. And graphically, it looks like this. At the price of 100, you get a demand of 380. So each dot along the line of demand curve represents a relationship of a price level and the corresponding demand level. So that's what the demand curve represents. And then the question is, how do we find a demand curve? I mean, I've given you a demand curve here, but how do you find one in reality? And here's the most common way to get a demand curve. Let's say you have a full history of supply and demand over time. So what we have here on the horizontal axis is price, and on the vertical axis is demand. Let's say historically you have set the price at different levels. At each time period, you observe the demand at a price level. Let's say at this point, the price is about $800, and you observe the demand of 300 units at this price level. So you can put down one dot here. And each dot that we have in this scatter plot is basically one observation. Now, over time, we have many observations of the demand level at different price points. So in this scatter plot, we can use the existing observations to figure out how demand changes with price. What do? We put in a trend line. So as you can tell, this can be done in Excel. So we put in a trend line, and if we display the equation for this trend line, we're going to get y equals minus 0.1x plus 390. And that basically y is demand and x is price. So from this, what we have is essentially demand equals 390 minus 0.1 price. That is how we find the demand curve. And using a demand curve like this, we can actually find out what the profit actually looks like on a demand curve like this. So now I'm going back to the demand curve that I've shown at the beginning. That is demand equals 390 minus 0.1 times price. So here we're looking at the pricing of a vacation package. And the variable cost of offering a vacation package is $100. I've drawn the variable cost here. So if we price at variable cost, the demand is 380. So within this graphic representation, let's say if I already know the optimal price, that is the price gives us the highest profit. Let's say I already know the optimal price is $2,000. And then we know that on the demand curve, we can find the corresponding relationship between a price and a demand. So at $2,000, the corresponding demand is basically 190. And that's the demand at the optimal price level. And you can also plug in 2,000 here. It will be 390 minus 0.1 times 2,000. So that's 390 minus 200. That would give you a demand of 190. So now we have the optimal price, the variable cost, and we know the demand at optimal price. And the next question is, how do we calculate the profit? So the profit is equal to the price minus the variable cost times the demand, then minus the fixed cost. So that's the profit. And for now, let's ignore the fixed cost, just focusing on the profit part without the fixed cost. So when we plug in the numbers that we have, profit would be equal to 2,000, that's the price level, and minus 100, that is the variable cost, and times the demand at a price of 2,000, that's 190. So that is the profit. And we can use this graphic to display what the profit looks like. Let's look at this calculation. 2,000 minus 100 times 190, 2,000 minus 100 times 190. So that is basically the length of this times the height of this. So essentially, profit is simply the size of this rectangle. And since I already told you the optimal price is 2,000, which means if we shift this price around to the left by lowering the price, or to the right by increasing the price, what we're going to see is if we change that, and the new rectangle would have a smaller size than the size of this rectangle at the optimal price. So that is the graphic representation of the optimal price and the maximized profit. Now let's come back to how this is calculated. So how to calculate the profit. And the formula, as we have just shown, is the profit is equal to price minus the variable cost. So that gives us the profit margin. And the profit margin times the demand would give us the total contribution. And then if we deduct the fixed cost from that total contribution, we'll get the net profit. And the formula we have for demand, given the demand curve, is demand equals 390 minus 0.1 times price. If we plug in demand into the profit function, we have profit equals price minus 100, that is the variable cost, times 390 minus 0.1 times price, and then minus the fixed cost. From this equation, we want to calculate the optimal price, that is the price level that maximizes the profit. So the first question is, does optimal price depend on the fixed cost here? And it's not difficult to tell that it doesn't, because whatever you produce from this area would deduct a fixed number of fixed cost. That gives us the profit. So wherever this profit component without fixed cost maximizes, that's where the profit maximizes, because fixed cost has nothing to do with it. So interestingly, as you can tell from this formula, that fixed cost actually has nothing to do with the optimal price level. And when you calculate the optimal price, you can safely ignore the fixed cost. So the next question is, given this formula, price minus 100 times 390 minus 0.1 times price, what does the relationship between price and profit look like? And here is what the relationship looks like. So what we have is price, profit. So in the lower range of prices, when price increases, profit also increases with price. But at a certain point, actually that certain point would be the optimal price with the maximum profit. At a certain point, once price goes higher, profit actually would go down. So it's not that the lower the price, the better, nor is it that the higher the price is, the better. The optimal price is somewhere in between out there. And the reason, when you think about it, is because of this. Profit has two components. The first component, the profit margin, it increases with price. The second component, the demand, it decreases with price. These two components, when they balance out, is where the optimal price level is. So if the price is too low or too high, in either case, it would lead to inferior profit. And instead of us trying to figure out where this optimal price level is, we are going to use Excel's solver to figure out the optimal price. Here's just a general idea of how Excel's solver works, how it finds the optimal solution. Within the solver, it actually takes derivatives of this curve, and with the derivatives, it tries to find a slope to climb up. I mean, the way you can think about it is basically Excel has this little guy within the engine, and this little guy would basically climb up the hill. And when this little guy reaches the peak, it would realize that if it goes further, it will start to go down because the profit is going to get lower. So it decides that this is where I should be. This is the best point to maximize my profit, and that is the optimal price level. So that's basically what Excel does within the engine. The good thing for us is we don't have to deal with how this process is done. We just need to specify the interface on Excel, and the solver would give us the results. And on Excel, there are a couple of optimization tools, and one of them we have used is GoSeek. And the main one that we're going to use from here on is solver. And the difference between GoSeek and solver, and GoSeek is a relatively simple engine. It tries to basically set a target value, so set a cell to a value by changing another cell, let's say price. For the rest of the semester, our main focus is on solver. So on the right is the interface for solver. We are going to have separate videos using Excel examples to introduce how solver is actually implemented. But in this lecture, let me just give you an overview of the different components on solver's interface. So once you open up Excel's solver, so this is in data solver, once you open up this window, the first component of input is set objective. And this is where you put the cell that represents what do you want to achieve. Are you going to maximize the profit? Are you going to minimize the cost? Do you want to set the target specifically to a value? So this is the objective you set. And the second component, after you set the objective, is how are you going to achieve the objective? Are you going to vary the price, the effort, the location, etc.? So these are the cells that would vary in order for you to achieve your objective. So in pricing, what we are going to do is we're going to change the price and find out at what price level we can maximize the profit. And once you have the changing cells, such as price, you need to tell Excel's solver engine what range does Excel look for answers. So is it between $5 to $50 or $5 to $5,000? What is the range? What are the constraints that you allow Excel to search the answer for you? So you want to give a meaningful range here for price. And the better the range you give, the more efficient Excel will be at solving the answer for you. And the last component of solver is to choose a solving method. So what method do you use to optimize the price? And we'll look at the details on the next slide. So Excel's solver offers 3 solving methods. First, by default, is GRG Nonlinear. This is where we start. And this solving method, generally speaking, is fairly fast. It solves smooth or curvy type of problems. The calculations can involve square, exponential, logarithm, power, etc. An example of a smooth problem is this. You have a smooth curve between price and profit. So that is a smooth problem. And the smooth problem can go like this. It can go like this. But it cannot go like this. It cannot have sharp turns. And the second solving method is called simplex LP. Here LP stands for linear programming. And since this is a general introduction, I try not to get into more details, but generally speaking, let's say you are trying to win the war, and the war is, so that's your objective, and the war is a function of how much butter you can produce and how much gunpowder or guns you can produce. Here, when we call a linear combination of butter and guns, what we have is basically when you calculate the butter and when you calculate guns, butter and gun just in their original form. They don't multiply each other, they don't square within themselves, that you don't have butter square. That gives us what we call a linear problem. So that's what linear programming solves. Since both profit margin and demand involve price, so price actually is squared. That is why we require a GRG nonlinear to solve instead of simplex LP. And the third solving method is evolutionary. Remember I mentioned GRG nonlinear cannot solve the problem when there's a sharp turn in the relationship, and that's where evolutionary comes in. So generally speaking, it calculates the problems when you have functions in Excel such as if, sum if, average if, count if, maximum, minimum, or match, all these functions that leads to a sharp turn. An example would be if you have quantity discount, so the price changes at a certain demand level. Here you're going to have sharp turn of how profit varies with price, then you will need an evolutionary solver to solve it. All we need for now is the GRG nonlinear, the default solving method. There's one more thing within GRG nonlinear that you're going to see when you click this options button after you choose the GRG nonlinear engine is this. So within the option of GRG nonlinear, these things don't matter, you don't really need to change them. The only thing that you should check is the use of multistart. And what does this mean? Let me give you a graphic illustration. Let's say we have a price and demand relationship that is like this. So there's a smooth curve that goes up and down, and that's profit as a function of price. And if you don't use multistart in GRG nonlinear, what happens is when you climb the mountain, the little guy is going to start somewhere. So let's say the little guy happens to start here within solver. And if the little guy starts there, the little guy is going to climb to here. And within solver, the little guy would find that if I go further, the profit starts to decrease. So this is where I should be. So I'm going to stop here. And it's going to get trapped at a local optimal point without being able to climb to higher hills on the other side. So what the multi-start does is multi-start is going to climb from different spots along this line. By doing that, chances are you're going to find the real optimal price point. That's why it's usually a good idea to allow multi-start when you use the GRG nonlinear solving method. This is especially relevant when your profit function is complicated and you are not sure how the curve shapes up. For the current problems that we're solving, there's only one peak for profit, so we're relatively safe even without multi-start, but overall it's a good practice to allow multi-start. All right, one more thing. When it comes to pricing, there is a strategy very commonly used in marketing. It's called product tie-in pricing. Sometimes it's called loss leader pricing. So the idea is this. People buy razors, and then down the road, they're going to buy more blades to be used on the same razor. You have a very specific interface that connects the razor and the blades. So when consumers buy your specific brand of razor, they have to buy more blades from you. So you make a profit from both the razor and the blades. And the idea here is because blades create a lot of downstream profit. So you want to price your razor at a very low price point so that will encourage more people to buy your razor. Remember the demand curve. So when you price the razor price low, you get more people to buy the razor, and more people would end up with even more blades. So that is what we call product tie-in pricing. Pricing razor price low so that you can sell more blades and overall achieving a higher profit level. We're going to have an Excel example specifically for this. And the idea of the calculation is this. First, you can use the historical data to get a demand curve for razors. And then we do two different calculations. First, we focus on the profit from razors only, and we find an optimal price for maximizing the profit from razors alone. And then we can calculate how much total profit we get based on that. And second, we are going to do a different price optimization where the profit is the total profit of razors and blades. And then, because this profit has factored in the profit from the razors as well as the blades, then we can find a different optimal price that maximizes both profits summed together. And then we're going to compare using these two different methods, how are the optimal price levels differ from each other and how much more profit we may be able to gain if we optimize the price based on the overall profit. You will find more details in the Excel video separately. Thank you and keep up the good work.